Good morning, good afternoon, good evening, wherever you are, and welcome to this session on accelerating Flash for a competitive edge in the cloud and beyond. As you know, this presentation is part of a much larger track that is focusing on new storage technologies, and zone namespaces, ZNS for simplicity, is a big part of it. So this session is focusing on that part of the technology as well, but is a little bit different from the conventional ZNS topics, because we are not going to dig into details on how ZNS work. There are other sessions that cover that. We have excellent speakers, and I really recommend you to follow those presentations if you want to learn more. Because what we want to do over here is more to step backward and look at what type of benefit and advantages the user will see from this type of technology. Meaning, if I am an end user, I'm not a storage expert. I'm running a real life application to do real life work because that's where my money go. Why should I look at this? What value is for me there? And so we'll cover a little bit of that, but Micron is a SSD manufacturer, so we also focus specifically on the value where we can provide more contribution. And there is a new technology coming out, as you are aware, called QLC, quad level cell, which is having some major advantages from ZNS, and that is what we'll cover over. So looking from an agenda standpoint, we are not going through the ZNS technology as said, but we'll just mention some of the key tenets just to understand what is good and what is bad and what is in the technology and what is needed to make QLC viable, and therefore why ZNS is going to help on that. After that high-level introduction, we'll really dig into the real meat of it, which is look at applications. And for that, we picked two applications, one more modern workload, meaning more cloud-oriented, and another one more traditional, something that has been around for many more years, so design in different ways, and trying to see what are the advantages. In a modern workload, we basically used Apache Cassandra. This is a very well-known, popular NoSQL database used in a lot of cloud applications. And we are running a standard benchmark, YCSB. This is a Yahoo Cloud Server benchmark, so a very typical cloud-oriented type of environment. So we want to point out the values of ZNS and QLC in this space. And in the case of traditional workload, we'll do something similar, but using more traditional setup with MongoDB and running the more traditional TPC, Transaction Processing Council type C type of benchmark. It has been around for 30 years probably, so it's very traditional. On top of that, we also added one piece of software that is a good companion to ZNS, and it's called HSE. HSE, we'll see it a little later on, is a heterogeneous storage engine. It's an open source that Micron has contributed to the open source community, and because of its nature, is a very good fit for ZNS. And then we'll mention a little bit about future work. ZNS is new, the QLC is new, everything is on the move. So we'll point out some of the good and some of the bad, and most of all, some of the other where some work is still needed to make further progress. So without much ado, let's move into this, and let's look to what do we care? I mean, why the end user should care about the ZNS? Well, at the end, when you look for performance, there are two main aspects that people focus. It's performance, meaning how fast I can run something, or it is life, meaning how long my device will live, how long will it take because I have to replace it, and so on and so forth. When we look at this in this presentation or in this work, we decide to focus more on life and not performance. The reason is because performance is a difficult topic. If we are really focusing on one specific user case, yes, absolutely, you can focus on performance and tuning. But when you look to general technology, performance have contribution everywhere, not only the SSD. It depends on the system where it runs on, the number of processor, the type of processor, the RAM, database, and so on and so forth. And if the storage is not 100% the bottleneck, you only get diminishing return. So the idea is performance is important, but we'll focus on that on specific tuning, because it is a very global type of tuning, impacting too many parameters. Life, instead, is what really the SSD can pull out, and it is 100% consumed and 100% valuable for storage. And what we mean by that is that every SSD has an expected life, which is based on its own endurance. And depending on the workload, some device may last longer or may last shorter. And this is becoming, as we'll see, a topic with QLC. And ZNS is really going to help over here. Life in this space will be through this reduced media management. We'll see in a little bit. And as an outcome, we'll give more flexibility to the media selection, which for an end user, if I were an end user, I will try to get the cheapest device that meet my requirement. And QLC is definitely a contender, assuming that we can meet all the other parameters, and that is where ZNS will help a lot. So let's look a little bit on what's happening and why this is a topic. Not all workloads are suitable for conventional SSD with QLC. This is an interesting statement, and is due to two different aspects. The first one is new technology with higher bit densities suffers in endurance, meaning the life of the technology, the more bits you pack, the lower the margin, the shorter the life. This has always been true. SLC was longer lived than MLC, that is a longer life than TLC, and so on. But the interesting thing is that until now, SLC was replaced by MLC with lower margin, and TLC replaced MLC with even lower margin. QLC, in some cases, will have negative margin, meaning it cannot be an obvious replacement for every single workload. In some cases, simply negative. What does it mean negative? It means it will live below the expected life of an SSD, and that is extremely problematic because of life management, because of cost, because it means that you have to replace more often. So this is really something that has to do with the technology, and us as other NAND vendors are doing everything possible to improve it. But there is a limit on the physics there, so we can't go beyond some of the technology aspect. The other area, which is really interesting though, is how does SSD manage data? Remember, SSD today are still a derivative of fast hard drives. You know, the software stack, the data location has not changed much in 30, 40 years. And what worked for hard drive may not work for normal conventional SSD today. One of that has to do with the fact that the data come from the system in random order, and NAND have to write them sequentially. Somebody has to do that data management. And that data management today is done by SSDs. And through that, they do a lot of data movement, and they create what is called write amplification. What is a write amplification? Means so many data comes in the SSD to be written, and a multiplier of them is written in an NAND because you have to move them around. You know, you write data the first time you write it, then you have to move it around to maintain the mapping, and you write the second time, and then you move that again, and for the third time. The ratio between how much NAND write and SSD write happen is called write amplification, which is a key aspect over here, because write amplification is basically reducing the life of SSD. But what I mean by that is that you have a NAND that is capable of, let's say, 1,000 writes, and it has a write amplification of 3, means that 1 write come in, and 4, the one coming in plus the 3 of management are in the back end. So actually, the system only see 1/4 of the write. It's like his life is reduced by a factor of 4. This is a very big problem for QLC, and this is where new data layout are needed to be able to avoid this fantastic and incredibly large data life reduction. Why does ZNS help in this? Well, ZNS helps because it transfers all this data management to the host, making it more efficient. So the pattern coming to ZNS is really sequential. And this is leveraging the fact that the host will combine his own mapping with the physical device mapping, making a more efficient map, and will result in a reduced write amplification, which in turn, lower write amplification means proportionally longer SSD endurance and life, better performance, even though it's a side effect, and most of all, will enable these new technologies. So this is why ZNS is key, because through write amplification reduction, it can extend the life of a QLC SSD. So what we did, we built a prototype. The prototype that we built is using an existing SSD that Micron has been shipping for a while. This is called 2300. Interesting enough, we picked a client grade, and somebody may raise an eyebrow at that, but there is a reason there. Actually, there are two reasons. One, we are developing and working with new technologies. We started this when ZNS was not a standard, working with NVMe consortium, working with partners, and we wanted to have a very stable platform. So we want to have something which is stable on conventional SSD, where we can just change the ZNS part and make sure it works. So it had to be a stable SSD. On the other side is that we want to make sure that everything is the same, including the over-provisioning. Over-provisioning is a big contributor for write amplification, meaning the higher the OP, the lower the write amplification. And what ZNS has is pretty much a zero over-provisioning. And in enterprise, zero over-provisioning doesn't exist. So client grade can do that. And we pick that so that we can really compare Apple with a zero OP NAND and see what happened. So we build this prototype. It's built on TLC, but it will work exactly the same on QLC. It's completely independent. We pick TLC for stability. It's a 2 terabyte. It's about 5,000 zones of 400 megabyte each, just to give some idea. The number of active zone and open zone are for people that really care about details on ZNS, how it works. Not really relevant at the end, if not for performance aspect. And we want to do is that to run a comparison of the two setup, conventional and ZNS, for all the benchmark. So let's get into the benchmark that we did. So what we did is that the first one is, as we said, Apache Cassandra. So what we did over here, this is a layout of the stack. Basically, we use Cassandra. Cassandra, we pick it completely unmodified. There is not one line of code that has been changed. This is absolutely standard. And on that, we use a file system, BetaRFS, quite a popular, where we had to do changes to support zone, because BetaRFS is designed to support, conventional namespaces, does not have the concept of zone. So we modified it to be able to support the zone namespaces, to run a garbage collection, and to do this backend of operation. Interesting enough, the only thing that we did here to associate file and zone is simply pick file at Cassandra write on the same directory timestamp. So we are simply saying all the files that you create within a specific directory goes on a zone or a set of zone, and that's it, nothing else. So it's still open to a lot of improvement, but we want to show how much improvement is just from these simple changes. Then there is another layer which deals with the zone itself. We call it DMZNS. This is a variant of an existing device mapper, which is called DM Zone. But we started that thing was not really available yet. So we made all the changes to make it work with ZNS and our prototype. So this will be distributed through open source and will allow simply ZNS to run as a device mapper, like in many other Linux open source. And finally, we use our prototype for the data. One thing that is open for debate is the use of conventional namespace for metadata. There is a big discussion ongoing in industry whether it's needed or not. We decided to use it because it makes the implementation from one side simpler, but most of all, the number of changes for the end user is limited, so limits the risk for the end user. Can be improved, but that's probably the safest option as of now. So once we have that, let's get into the benchmark. First thing that we did is that what Cassandra called write stress. This is not a real life. This is just to see how things work, just to get familiarized with that. And basically, he writes, about 300 gigabytes. We have two different setup over here. The setup called 2300 is a conventional Micron 2300 SSD. The one that is called ZNS is, of course, with ZNS. And there are the two charts over here that show exactly the same type of profile. I try to keep the scale consistent so you can appreciate the difference in sizing. And basically, they show in green how many writes goes to SSD, in blue what gets back to the NAND. And you can see immediately in the conventional SSD how in some area like this over here, there is a lot more write to the NAND than to the SSD, and this is because of the garbage collection kicking in. So it is periodic, every so much time. What happened here is basically that we write 300 gigabytes to the SSD, but NAND write 940. With the write amplification, as we said, the ratio between what is written in NAND and what is written on the SSD, about 3.09. ZNS, well, you see that the two lines are pretty much the same. The green line and the blue line almost perfectly overlapped. And actually, we wrote 294 gigabytes in this case on the SSD, and 334 went to NAND. Now, keep in mind that this also has all the mapping and garbage collection in the host. What results on the NAND is 2.13 write amplification. So the ratio between the two of them is about 2.7. What it means from a practical use is that a device running ZNS, running this exact workload, will live 2.7 times longer than not the one on conventional SSD. So for example, if you have a QLC that in this condition may live, let's say, 2 years instead of the 5 that you expect, well, the moment that you switch it to ZNS, all of a sudden, without changing anything else, just moving to ZNS, life gets extended by a factor of 2.7, so it will live 5 or 6 years. So it can make the big difference between failing to meeting a requirement to absolutely meeting and sometimes exceeding requirement. So this is just the general setup. Let's look to real life type of implementation. This is YCSB. This is a third-party benchmark. We have no control on that. Is a Yahoo cloud server benchmark. And we see some of the same in terms of the difference between green and blue over here, but the distribution is more like real life. So you have a lot of more traffic. There is probably a lot of more override, which causes a lot of more write amplification. But if you look in numbers, at the end of the day, things are not much different. Yes, in this case, 2.68 is a bit better. ZNS is pretty much independent on what happened on the workload. And you can see on the green and the bluish line here. Big difference here, not much over here. And again, an improvement in life of about 2.4. So real life YCSB running on Cassandra, ZNS extend the life of a potential SSD about 2.5 times, 2.4 times exactly, which again, all of a sudden may bring life of this device into the range of viable application. One thing that we found a bit disturbing is this 1.13. I mean, good as it is actually not as good as 1.0 as we would expect it. So what we did is that we looked to, hey, how are the zone mapped over here? How does Cassandra use this zone? And this is a zone map. The way this works is pretty simple. On the x-axis, you have the zones number. So it is like 5,000 zones over here. The y-axis, this blue line, represent how much each zone is used. So line that goes to the top means 100% use. Line with ends somewhere in between, like over here, means that these zones probably are used like 60%. The white is empty space. And the line that are completely white, those are erased zones. They are not used, that are available to be used. So even just with this very simple implementation, we see that utilization is 95.2%. So it's extremely high by itself, but should be better. We could improve this. So 100% will probably be the target for this, or close to 100%, which would result in the write amplification of 1.0. So we still have work to do over here to improve this. The basic life affiliation as is already by 95%, so a huge advantage, but it still can still be improved. So the first thing that came up from this simple test is that everything else being equal, same hardware, same NAND, same over provisioning, ZNS reduced write amplification of a factor about 2.5, right? And this include all the garbage collection and management operation. This is important because, again, it dispels the false myth that moving the garbage collection to the host is just moving the problem somewhere else. Now you move the map somewhere else and they become much more effective and therefore can be better used. So basically, we can have a device that is 2.5 times more resilient may last 2.5 times longer, which means that we move from a negative margin, possibly for QLC, into ample margin and probably potentially longer life than people may expect. And this is on new workload. Now, one of the things that we were thinking is that, yes, but new workload are already designed with new concept in mind. So they're already designed for this type of solution. How about the more traditional workload? So let's look to MongoDB. This is the other one with HSE and TPC. Same type of slide. We'll do a little bit of different flow. The first one was more introductory. This one we're talking about, we want to look to TPC on MongoDB and HSE. So let's make a word about what is HSE. HSE is a heterogeneous memory storage engine. This is an open source code that Micron has released to the open source community. Is available for download for Linux community. And what it does basically creates sort of a tier storage, meaning given that the problem is having very large capacity devices which have low endurance, how about having one small storage high performance for hot data and separate the traffic from the large capacity cold data? That is what HSE does. HSE introduced this type of tiering, so it is independent from ZNS. You can run on every type of device, and actually we will compare with a real-life device and see how this allows both separating the traffic workload and improve the life of the capacity tiers and adding zones to that will further extend the life over there. Setup is the same. We're still using the same 2300 and the same ZNS prototype. For the tiering, we added one more device when it's needed, which is called 9100. This is a shipping device from Micron that is an enterprise high-performance type of SSD for hot data. Comparison, again, is exactly the same on exactly everything on the hardware and other provision being the same. So let's look at what happened. This is a bit of an eye chart with a lot of traffic. The reason of this that we want to show you is the separation of traffic. Just to have some background over here. The cold color, green and blue, are the cold tier. The warm color, the orange and green, are for the warm tier. More specifically, blue is cold write. This one here. Green is a cold read. Orange is a hot write, and red is the hot reads. In the case of when we run it on, you see this label here, we run only on 2300. Here there is no ZNS, no HSE. Then we run with same as above, only with HSE, so it is still 2300, but HSE that use the 9100 as hot tier. And then we do exactly the same on the left, making a progression here and replace the capacity with the ZNS device. The real mess of this slide is what happened to the blue color. Why the blue color? Because blue, as we said, is a cold tier write. So if we just use this workload, TPCC on MongoDB, see, basically, in this case where there is no hot and warm, so it's one color only, this red line is pretty active around, 100 megabytes per second. So you can see there is traffic here. Now, HSE by itself, see what happened to the blue line, is reduced to almost zero. Not zero, there is something over here, a little bit peak here, but sometimes there are huge peaks there, right? This huge peak is because being a tier, you have to swap data in and swap data out. And so you see what is the impact here. When you go to ZNS, well, if you compare to the left, it's sort of the same, but there are no more peaks. All the peaks has been cut down, and all these peaks of write means much lower write, and therefore, much longer endurance. So at a glance here, I can show you why the 2300 may be limited because of this workload, and why HSE is helping, first step, and with ZNS is making this really way better. So let's look to the write amplification. Here we did in a bit different way that not with the previous experiment with Cassandra, because write amplification is not a number, is actually a combination of numbers and they change in time. So we are working a little bit more into how write amplification work over here. First of all, there are two different types of write amplification. What the device, meaning the SSD, creates, this slide, and what the host create that will be in the next slide. So if we look just to pure SSD, if we look to just 2300, you see the write amplification moves this way. The average is about 2.3, sorry, write amplification. If we add HSC, the same one has a completely different type of behavior. This is like, it's just another application that is in between. And it helps reducing it though. It's about 1.9, meaning that the hot tier is filtering out a number of writes, but still they are scattered around. So there is still a pretty high write amplification. When you go to ZNS, well, yeah, there is a write amplification. You may not see it, but it's here, very down to the bottom, flat line, absolutely as close to zero as possible. 1.1 should be 1.0. Same as in the previous discussion for Cassandra, can be further reduced. But you can see at a glance that the write amplification on the device get significant improvement, and therefore the life get improved in proportional way. And this is on the device. But given there is a host garbage collection that happen at the host now, what does it mean for the system itself? Well, let's look at over here. This is the total write amplification, meaning what the application sees. This includes all the write amplification created by MongoDB, by HSE, by the SSD, everything. And it's interesting for 2 or 3 different reasons. The first is, what is the number over here? On a normal SSD, you have a total write amplification about 11.1x. 11.1x means that for every kilobyte that you write, well, actually 11.x kilobytes are written on the NAND. Or if you can read it the other way around, it means that whatever amount of life you have on your SSD, only less than 1/10 of it, 1/11 of it is actually available to the system. And that is what is killing a lot of QLC application in real life. It's, you're reducing over an entire order of magnitude the life here. See, if you add HSE, things change a little bit, but not so much. From 11 to 10, it's a bit of reduction. Why is this? Is not wider gap? Because here, as you said, there is a lot of data management that still has to be done by HSE. When you go to ZNS, well, there is write amplification. There is mapping here. The entire map that was moved to HSE happen in HSE, and all the his own native is still there. So it is a 6.7. But still, if you compare from 11.1 down to 6.7, well, there is still a significant improvement of write amplification. We'll see the detail a little bit later, but here the chart wants to show how much better this is. The other thing I want to bring up is that we ran this benchmark for about 5 hours. But if we look over here, the data keep growing. So 5 hours may not be enough. So we say, well, let's try to run it and see what happens if we run much longer. So if we look to a much longer, this is what we get. We only use the 2300 native and the one with ZNS. We skip the one in between because this benchmark like 3 days, 50 hours, 2 days, each one over here. And one of the things that you notice that, yes, write amplification can keep growing to about a little bit, half of that, probably for 20 hours, then start settling down. Same thing for ZNS. After about probably 20 hours, things settle down. So these are probably more representative for long term. And the interesting thing is that ZNS is still 6 point something, has not changed much. But this one here, regular one, keep growing and grow up to 15 on average. So really, if you want to run this type of application, ZNS, compared to the same device with conventional SSD and with HSE, create a write amplification improvement that is about 2.3x. So, 2.3 times longer life. One other interesting thing here is, you want to say, okay, what is HSE doing? So let's spend a little bit of time on that. Basically, HSE is separating, we said, cold and hot data. So we are, again, charting 2300 over here, and then the same at 9100 plus 2300 and 9100 plus ZNS. The column on the left is how much the media are used, and the column on the right is how much data really written there. So when we run the benchmark for about 5 hours, just to give you an idea, we use 800, the database uses 800, a little bit more than 800 gigabyte, and writes generally a little bit less than 5 terabyte on that. When you start HSE, what you expect is that you have a small hot data, which are red over here, which is smaller than the green cold data, but it absorbs most of the write. So the number of writes are much bigger on the red and not on the green, which is exactly what is happening over here. So the hot tier is smaller and there's more write. And just to give an idea, we have like 200 gigabyte of hot tier, which takes, 4,500, probably like 80% of the writes. Moving to ZNS, this is further reduced. We actually use an even smaller hot device, less than, probably 150 gigabyte out of a terabyte. And this keep absorbing the same amount of write. This is why all the traffic get reduced and why the life can really be extended to make this device really viable. So in summary, what this benchmark is doing is sort of confirming the same data that we have seen from the other benchmark. Life improvement, I think, was 2.5. WAF was 2.5 improvement with Cassandra. It is 2.3 over here, still about the same order of magnitude. Remember that write amplification still on SSD is still 1.1, which means that the data mapping can still be improved, which means this data still can be improved. But, basically, all of a sudden, we are giving a 230%, 250% boost to life to the SSD, and this will bring a lot of QLC into the deployment level for this type of devices. So QLC really would get a very, very big benefit of this device. So this is just a summary, and it's pretty much confirming what I just said, that both traditional and modern workload, one addressing cloud, the other transactions, one design with modern SSD in mind, the other one more traditional, all of them can benefit in sort of the same type of way from this type of solution. There are also other traditional file systems that will give probably much more advantage because of being traditional, designed without any of this in mind. It is more work, but even a bigger advantage if we do that. So there are a lot of further tuning we can do over here, either in the SSD or in the open source or in the standard. And I would invite everybody that has been listening to this presentation for so long, for this 30 minutes now, that is interested to contact me or contact your representative in the standard body or in the open source, because there is a lot of potential cooperation we can further do over here and really make QLC as a technology and ZNS as a data layout and the software stack provide a really modern stack that will allow the 2020 decade type of workload to really benefit and extend their own capability with this new SSD technology. Thank you very much for listening to all this presentation, and please feel free to contact me if for any question you may have. Thanks a lot. Have a good day.